At the end of Chapter 3, there's a table, Table 1, that pretty much summarizes the contents of the third chapter on 95% confidence intervals. The problem is that that table is a little bit hard to understand, and so what I've done is I provided a figure that's meant to represent what's in that table. The problem is that the figure is not that easy to understand either, so that's why I produced this video. So what this figure shows are the 4 different scenarios in 4 different panels. So here we've got an attempt to estimate the population mean mu when the population standard deviation is known. And here we've got an attempt to estimate the difference between 2 population means when they've got the same standard deviation and it's known. Here we're estimating a single population mean again, but this time the standard deviation is unknown and it's going to be estimated by the sample standard deviation. And here we put those two together. This is the most likely scenario you're going to encounter where you're interested in estimating a 95% confidence interval on the difference between 2 population means where they've got the same standard deviation, but we don't know what it is. So those are our 4 scenarios, and we're going to begin with the first one, a situation in which we're trying to put a 95% confidence interval on the population mean, our estimate of the population mean, when the population standard deviation is assumed to be known. So we're going to start here, and we're going to assume that our underlying population is normally distributed with some mean mu and some standard deviation sigma. So what we can do is we can take a bunch of individuals from this population, calculate their mean, and put it on a number line. Then we take another bunch of individuals, another sample from here, calculate the mean, put it on the number line right there. So we repeat this process an infinite number of times. So what do we get? What we get is a probability density function for the set of all possible sample means. And what are the features of that probability density function of all possible sample means? All sample population means are normally distributed. They'll have the same mean as the underlying population, but the variability of sample means is going to be less than that of the underlying population, because when we take our samples, the larger and the smaller individuals are going to tend to cancel out. Some other things worth noting. This is a probability density function. This thing is a probability density function. But it's the probability density function of a sample statistic, so we can refer to it as, get rid of that line, we can refer to that as a sampling distribution. And it has a standard deviation. We have a special term for the standard deviation of a sampling distribution, and that is standard error. So with all that in mind, we can start off with y bar, we can subtract mu, we can divide by standard error, and that gives us y bar minus mu divided by the standard error. What do we know about that? We know it has a standard normal distribution. And the advantage of a standard normal distribution is that it permits us to use a Z table. So if we think about this particular value, and we've got these two values, minus Z alpha over 2, Z alpha over 2, where alpha is, we can think of it as being our permissible error, then we can say that the probability of a value like this lying within this range, plus or minus Z alpha over 2, is going to be equal to 1 minus alpha. So what we have here is a geometric representation or a graphical representation. We can illustrate that algebraically down here. So we're saying the probability that this thing here lies between minus and plus Z alpha over 2 is equal to 1 minus alpha. And once we know that's true, we do our dancing around the inequality sign, and we arrive here. So that's the second scenario. In the second scenario, we're interested in getting a 95% confidence interval on our estimate of the difference between 2 population means when the standard deviation is the same for the 2 populations and it's known. So we're going to start here with our two populations, y2, y1. They're normally distributed. They've got different means. They have the same standard deviation, and we know what that is. So as before, we could take a sample from this guy, take a sample from this guy, calculate the two means. The difference between the two means we put there. We take another sample from this guy, another sample from this guy, take the means, the difference between two means, the difference between two means, those two sample means goes there. We repeat this an infinite number of times. So what we're interested in doing is thinking about theta. Theta is the true difference between those two population means. Our estimator of theta is theta hat. It's shown here. When we go through this process, what can we say about the distribution of theta hat? It is normally distributed. It's going to have a mean, shown here, of theta, which is exactly the same as the true difference between those two population means, and it's going to have a standard error. The standard error is given here. So then what we do is a very similar process to what we saw up here. We can subtract theta, divide by standard error. That gives us this. This thing has a standard normal distribution. Once we've got a standard normal distribution, we're off to the races, because we know that 1 minus alpha would be the proportion of these guys that would exist between minus z alpha over 2 and plus z alpha over 2. So this is a graphical representation. Here we've represented the same thing algebraically. The probability that this guy here lies between minus z alpha 2 plus z alpha 2, probability that lies here is equal to 1 minus alpha. Once we've got this equation here, we just dance around the inequality sign and wind up for a formula for a 95% confidence interval on the difference between two population means when the standard deviation of both populations is the same and known. Now what we're going to do is the third scenario, where we're trying to get a confidence interval on the 95% confidence interval on our estimate of a single population mean, but in this case, the standard deviation of the underlying population is unknown, and it's going to be estimated by our sample standard deviation. So what I've done here may not be terribly obvious. So what I've done here to save space and to simplify matters, I've taken this diagram right here. Taking this diagram right here, and I've just copied it right here. So this thing here is just a copy of this thing here. So we begin at this point. The difference between this scenario and the scenario up here, of course, is that now the population standard deviation is not known. It's estimated by the sample standard deviation. So what happens is we can no longer assume we know what sigma is. We replace our estimate of sigma, we replace our known sigma with our estimate that's derived from the sample. So now we replaced sigma with s. But because s is itself a random variable, that introduces more variability in the relationship, and therefore we can no longer use a normal distribution. So we don't use a normal distribution. What we have to say is that when we calculate y bar minus mu divided by the standard error, it's not going to have a standard normal distribution. It's going to have a t-distribution with, this is nu degrees of freedom. But once we've got that, the process is pretty much the same as what we showed up here, namely that we can have our minus t values and plus t values that we get from our t table, and 1 minus alpha is the proportion of these guys that will lie between minus t and plus t. So again, this is the graphical representation. It's represented algebraically here. So if we think y bar minus mu divided by standard error, the probability that it lies between minus t and plus t, probability that it lies between minus t and plus t, that probability is equal to 1 minus alpha. We dance around the inequality sign, and that gives us our final answer that we actually use to solve problems. And finally, we come down to the most complicated but the most realistic scenario, where what we're interested in doing is getting a 95% confidence interval on our estimate of the difference between two population means when sigma, the standard deviation of the populations, is the same for both populations, but it's unknown. And again, what I've done here is not terribly obvious just looking at the figure, but what I've done here, similar to what I did earlier, was I took this little graph here, and I've just copied it down here. So what you've got here and what you got here are just copies. So we're going to start off here, because everything here is true, assuming that, as we got here, we've got two underlying populations that are normally distributed. Now, what happens is that unlike this scenario, in this scenario, we no longer know what the population standard deviation is. So whereas in this case, we had sigma squared and sigma squared, we no longer know what these values are. We estimate them with the pooled standard deviation. So as a consequence of using the pooled standard deviation as opposed to pooled variances, we use the pooled variances because we're using the pooled variances instead of the known variances. Now we can no longer use a standard normal distribution. Now we have to use a t-distribution. But again, once we get to this point, we just progress as before. We think of this value of theta hat minus theta divided by the standard error. The probability of that value of theta hat minus theta lying within minus t and plus t is 1 minus alpha. This is just a graphical representation. Algebraically, it's represented here. The probability of this guy lying between this value and this value, probably the theta hat minus theta divided by the standard error lying between minus t and the plus t, that probability is equal to 1 minus alpha. Once we've got that, we just dance around the inequality sign to come up with the formula that we would use when we actually calculate the 95% confidence interval on the difference between two population means when the standard deviation, the variance of the two populations, is unknown but equal and estimated by the appropriate variance or standard deviation from the samples. So that's just a very quick go over of that supplementary figure, which is meant to be equivalent to the table in your notes, but hopefully a little bit more understandable.